Welcome back to a new video. D3D12Ez here on the Vertex channel. Now in the last videos we have talked about like resources, uploading data to the GPU to then finally describe the input assembler. Now what the input assembler has been doing is it has taken our vertex data that we somewhere defined above here in like a struct and then the vertices in an array. We have then basically told the input assembler that's the layout, and the input assembler was assembling all of the data here, that raw memory data inside the vertices array. It was now assembling that into a proper like vertex with like structural data, and has basically assembled like this raw data into something meaningful. Now the next thing that we need to do is we need to actually take the data from the input assembler and process it, and we're gonna process it with the so-called vertex shader. The vertex shader is the next thing that comes after the input assembler, and the purpose of the vertex shader is to take the vertex layout from the input assembler and turn it into some meaningful data for the rest of the pipeline. In general, you can just get away with just using the vertex shader, and the idea is that the vertex shader prepares the data so that it is relevant for the rasterizer, so that it knows what to do with that. Because a rasterizer, guess it or not, it doesn't know position. Position is something which the rasterizer doesn't know, but the rasterizer does need to know a 4-dimensional coordinate for rasterization, where it only takes into account like 2 coordinates. That's what the rasterizer needs to know, and what we need to do in the vertex shader is we need to tell it what to do. And since we're going to talk about shaders today, we can already talk about the pixel shader while kind of like skipping the rasterizer for now. So the vertex shader comes like after the rasterizer, after all the geometry data has been turned into pixels, and that's similar to the vertex shader. The vertex shader takes like the raw vertices, turns in something meaningful for the rasterizer. The rasterizer outputs pixels, and the pixel shader takes them and produces a meaningful output for the so-called output merger. We won't talk about the output merger or the rasterizer today. Today we just want to talk about shaders and how we can write them. Now shaders in general are snippets of code that run on the GPU. As simple as that. It's just a piece of code that runs on the GPU that can be highly parallelized, whatever, to kind of like increase performance. So if we have like 3 vertices, these 3 vertices will be passed down the vertex shader simultaneously. So 3 vertices, 3 vertex shader instances, both running simultaneously, and the same also goes for pixels. And that's the general idea, right? The GPU is parallelizing the work. In here we have kind of like serialized all the data. We have crafted the vertex in like a serialized fashion. We have created all of that descriptors in a serialized fashion, so at some point all the data is on the GPU, and now we can put them all into massive parallel processing so that we can get things done fast. Now what we want to do today is we want to write a shader, so a bit of code for the GPU. Vertex and pixel shader. Let's start by the vertex shader. First of all, what I want to do is I want to create a new folder here in my Visual Studio solution, and I want to call them shaders. Now the shaders folder will obviously, as the name suggests, contain all of our shaders. So now I'm going to click on a new item. You're probably, if you're using a recent version of Visual Studio, you're going to get that toolbox. That's kind of like suggesting you a name here without like all of these templates. What you want to do is you want to click on the Show All Templates button, and this will open up the kind of like legacy, old school Visual Studio new file dialog. What you want to do is you want to go down here to HLSL, High Level Shading Language. This is the language in which we're going to write our shaders. And what you can see is we have many kind of like templates available for shader programming. We want to write a vertex shader. The first thing that we want to do is write a vertex shader. We're going to keep the name. It's going to be called vertex shader.hLSL. And what we can do is we can click add, and then the shader will be added to our project. Now you should get syntax highlighting here. If you don't get syntax highlighting in here, you need to install the HLSL tools. It might already suggest you up here in like a yellow box that you want to install it, and you can click yes, and it's automatically installing it. If you are not getting some syntax highlighting and you want to have it and you don't get any prompts, you need to make sure that you're on the latest Visual Studio version, and then you can go to the Visual Studio installer and install the HLSL tools for shader programming. Now, as you can see, if we are creating a vertex shader, it already comes with a template, and that's already good. We want to take the template and make it better. Now, I'm going to construct it code from top to bottom so that you can kind of like get a hang on what we are doing. Now, in general, the shader is similar to like C++. It's actually like I think a Clang-based compiler, as far as I know, the DirectX compiler. And what you're going to write is you're going to write some C/C++ code in here. It's more like C than C++, but there are a few features that look more like C++ than C. Now, in general, the Vertex shader is like any other C application. It is basically, based out of or composed out of functions. So you can see you can create a main function. And that's also how shaders work, right? You can actually specify and give them different names than main. It's actually something that's configurable. If I would go in here in the properties, you're going to see that we have like this HLSL compiler tab, and you can see that we can give it an entry point name. And in this case, it's called main. And it's kind of like the most common thing that you're going to do. Now, inside that main, you're basically going to execute code, then everything else. Now, in general, depending on the shader that you are writing, you're going to have different input and output layouts. Now, one thing that's different to like normal C or C++ programming is that the input and output types are meaningless. Not types, but the input and output parameters are meaningless. In general, if you're writing a shader, it's completely meaningless what arguments you give the function or what output you produce. It is completely meaningless. So if I would take the example from above here, if I would have as an input a float 4 position, this would be completely meaningless. Also, if I would return a float 4 here, it is also completely meaningless. In DirectX 12, or in general like shader programming, you need to bind your arguments to semantic names. Now, we already had the term semantic name above here. Here in the input layout, we described a semantic. In this case, the semantic was called position and was a 2-dimensional 32-bit float. And this is basically the signature that we need to replicate inside of our shader. So the input or the input layout is the input for the Vertex shader. And what we do in the Vertex shader is we need to bind, for example, this float 4, which is actually a float 2, since we are only using 2 components. We need to bind that to a system value semantics. In this case, the semantic is called position. You can see float 2, this is the data type, RG32, 2 components, float 2, name is position, can be like everything, that would also be valid. However, of course, we want to keep it simple. And what we tell it by these double points here is we tell it that it is mapped to the semantic name called position. And the semantic name is coming here from the input layout description. This is how these two things get bound together. Now, what we need to do here is we need to produce an output. And the output could be anything. We could write a custom struct to output with something. We could use just a plain data type like it was used here, a float 4. We can really do everything that we want. The only thing that's really mattering is the binding. In this case here, for the template, the output has been bound to something called SV position. And actually, if you hover over that, you can see that you already get a bit of a description what SV position is. Because actually there are special values. Everything which has like this SV prefix, like SV position, if I would quickly look this up on the internet, you can see that the Microsoft documentation specifies down here some so-called system value semantics. And these system value semantics are semantics that are meaningful for the certain primitives of the rendering pipeline. Clip distance, cull distance, coverage, depth, depth greater equal, whatever, group index. And if I would scroll down here, also a SV position. And SV position, as you can see here, is defined as a float 4. So we need to make it a float 4. If we don't make it a float 4, it is a not valid system semantic and it doesn't work. And the SV position, for example, is used by the rasterizer to convert a triangle to pixels. And that's actually the only thing that the rasterizer needs. You have more options than available here that you might be able to set. For example, like viewport array index is a thing that's relevant for the rasterizer. However, you don't need to specify them. All of them have default values. The only thing that's kind of like not available as a default value is the SV position. You need to specify a position that's relevant. That's the most simple data set that the rasterizer needs. It needs a bit of an information, in this case a float 4, where to position the where to position the vertex on the screen so that it can be rasterized and 3 vertices can be turned into pixels. Now, this is kind of like the signature, and this is how we use it. I like to keep these names like not all caps, and it's also how they are defined by Microsoft, so I don't know why the template is specifying them as caps. Now, as you can see, we now have replicated our input layout inside of the argument. So the input arguments to the main function from the shader is now basically exactly what we have specified in our input layout. If we would specify more data here, so for example, like a position 2, just because I'm lazy, then of course I need to also specify that. I don't need to specify it. If I don't specify it, it's not going to be bound, but I can now specify that. And actually, this is even flexible. What you can do is you can also convert this into a struct. So I could call this vsin, this structure here, and then I would be also able to take these two things, put them into a, it's formatting automatically for me, put them in a struct, and then I could specify the vsin data. In is actually a special keyword in HLSL, which you don't need to specify, but you can also like say in vs data, then it's kind of like suggesting that it is kind of like an input value and not an output value, because you can actually also have your output values inside of the arguments, but that's advanced. I don't want to go into these. Also, like all of these struct layouts with like a structure and all of these things. This is something that we don't want to use yet. I want to keep it simple now, and so we are just going to do it like that. And of course, we're also going to remove that from here, because that's not how our vertex looks. Now you can see that we have now a nice little main function that we have specified for the shader and for the rendering pass, a simple rendering pass that we're going to do. This is completely sufficient, and this will be our shader. Now, what we need to do inside of the shader body is we need to convert this floating point value, which has like x and y coordinates, so it's a 2-dimensional float. We need to now convert this into a 4-dimensional float. And actually what we can do is we can use the constructor of a float 4. So as you can see, there are many like float types available. We can use the constructor of a float 4, and you can see that it suggests us x, y, z, and w values constructor function for a float 4. And since we are on shader programming, it's actually possible to construct this out of just the position, because this is actually a 2-component float, and then we just need to specify the z and the y. Or what you can also do is you can also access them. You can see it is suggesting you how to access the data from them, and in general, since we have an x and the y coordinate in here, what we want to access is kind of like the x and y. Now, the interesting thing on HLSL is that construction with like x and y works also in different ways. You can also specify xx to basically take out 2 floats from the same component. It is basically just a shorthand to get components. For example, if you would want to just get the x values, you could say xxx, and then this would be a valid float 4 here. However, that's not what we want to do. We want to take the x and the y, and the other values we want to specify by ourselves. How can we specify them? Well, just plainly as floating point values, and I'm going to specify them as 0 and 1. So the z coordinate is going to be 0, and the w coordinate is 1, and the w coordinate of 1 indicates that it's kind of like not a vector but a point. And in this case, yeah, it's something that you should get used to. If you're specifying a point, just specify it at 1. At 1, if you're specifying a vector, specify it at 0. This is kind of like some math stuff. And now, there you go. We have written our first shader. And now if I right-click them, I could hit compile and check if my shader compiles. And you can see compilation object successfully saved, and it has outputted that to my binary directory next to the executable as vertex shader.cso. CSO means compiled shader object, so this is basically the content of the shader. Now, what you can do inside of these properties is you can configure what shader model you want to use. And you can see that we are currently using a very old shader model. What we want to do is we want to use a modern one, like 6.6, for example. It really doesn't matter, but I would just take a recent one. And if you take a recent one, you might get a bit of information. Okay, we do not get an information. No output provided for debug embedding PDP. Okay, we are getting a warning, but we really don't need to pay attention to that. You can take a higher shader level, you can take a lower one. It depends on what features you want to have. It's kind of like the C++ language. Yeah, it really doesn't matter. Now, again, I'm just going to put it into it's some random default value. Now what we also want to do is we want to write the pixel shader. Pixel shader has also a template, also here with the same browser. Let's add this one, and you can see that the pixel shader also gets started with a default template, and we now also not going to modify the default template. We're going to keep it, and you can see that we are currently producing a float 4 here with all components set to 1, so RGB and the alpha component to 1, which is basically a white triangle. And actually, I'm not going to alter this at all. I'm only gonna make it lowercase because that's how it works. Now you can see that this shader does not take an input. This is possible. You can have shaders that don't take an input. However, you could also get one. What you can do is you could get the position that we got previously from SV position. This would work. I can get like the position here as SV position back in here, which is like coming out of the rasterizer. Because the rasterizer has used SV position, but it has not discarded that. So I could use the SV position as an input here, which we, as soon as we're going to have some feedback on the screen, also going to use to create a very interesting effect. Now you can see that the default template returns an SV target, which is a float 4. We can quickly take a look at the semantics again, and maybe let's take a look at SV target. And SV target is a float 2, 3, or 4, depending actually on the render target that you are using, because the SV target is writing to the render target, because it's then going to go to the output merger, and the output merger will write to the render target. So this is the actual pixel color, and depending on what render target you have bound, if it has like 2, 3, or 4 components, you need to have a different output value here. You can see that we currently use a 4-component one, and if I would go into my window.cpp and take a look on how we created our swap chain, you would actually be able to see that this is the correct format. Yeah, because we used R, G, B, and A. This is 4 components, so our render target has 4 components, so our shader also needs to return a float 4. Now you can see shaders, it's not really a big deal. You just need to get a bit away from the default concept of C++. The biggest takeaway from this video, from like shader programming in general, is that these input arguments and output arguments, they are all not bound. These are just like some floating data in structs, some floating data in variables. It is all not bound. You bind it by specifying this special syntax, which is like an extension to the default. I think it's actually C++, to the default C++ syntax of the compiler. They have made this extension to kind of like add these labels, these semantic names to your variables, and these metadata is basically compiled with the shader, and at runtime, or not at runtime, basically at the stage that we're going to create a so-called pipeline state, it is taking our input layout, it is taking the shaders, and it tries to mix and match these semantic names together. Also, when interacting between different shaders, if you have like a Vertex shader that returns an SV position, which goes to the rasterizer, it makes sure that we can also use it inside of the pixel shader here from the Vertex shader. In this case, it's not here with like SV position. It's just gonna be labels, and it's going to try to check if the member is available, and if it's available, it's going to bind it with the correct values. If it's not available, you're going to get an issue, and your pipeline state will not be able to be created. All right, so now we have written 2 shaders, a vertex and a pixel shader, very easily. And actually, the nice thing is, if I build my application, it will automatically compile these shaders as well. There's just one thing that I want to make sure: the vertex and the pixel shader, they should be on a similar shader level, right? We use 6, so now we should also use like the shader model 6 in general. I would in general recommend using like, yeah, in this case, just something modern is sufficient, yeah. So now we have used the shaders. Now I want to quickly show you where they actually are. Let's quickly reveal that in the File Explorer. Where is my button here? Open in File Explorer. And if I go into my one directory up, maybe we could do it in Visual Studio Code if I have it still open here. No, let's quickly open it up in Visual Studio Code, just that you can see it a bit better on where it is located. Now you can see that I have my build folder in here, and if I go to debug, you can see that here now my pixel shader and my vertex shader, they are next to the PDB and they are next to the exe file, and now we have the compiled shaders available. Now the next step that we need to do is we need to use this shader in our application. Now how do we use a shader? Well, our shader is currently on disk, so what we need to do is we need to load the shader. And what I want to do is I want to create a shader class. I'm going to create a shader class in the support directory here, and now I'm going to call that one shader.h. And what we're going to do in here is we're going to write a bit of code that is able to read them in. Did we use namespaces? No, I don't think that we did. So let's make a class shader so that we are able to to load a shader. Now, in general, what is required to load a shader? Well, first of all, what we need to do is we need to have a bit of a storage for a shader. I'm going to call this one mdata. So it's going to be set to null pointer, and then I'm going to have a size t in here, msize, which is the size of the shader. That's going to be set to 0. Now let's implement quickly how this will be implemented. We're going to have a constructor and we're going to have a destructor. The constructor will be a bit more special, but let's write the destructor first because it's simpler. Let's include c-string so that we have malloc and free available. And let's go in here. Or is it a cscdlib? I always forget these, but I think string is including them. So let's quickly free mdata here. Or is it? It is not. So it's cscdlib. Right, yeah, okay, it's in here. But what I do want to do is I want to do a quick plausibility check here. So if data, then we're gonna free it. So this basically cleans up all data. All right, so let's now take a look at the constructor. The constructor will take the name of the shader, and we are modern. Let's take a string view in here, and I also want to have the file system available, and we also gonna need Windows later on. I'm gonna spoil you, so let's include support wininclude here, and the constructor will take a std string view, and I'm gonna call that one name of the shader name that we wanna use. Now what the code is going to do is it needs to basically find the correct folder from which it shall load the shader, and when we found the correct folder, then we need to basically load the file from there. So how do we do that? Well, in Windows there is a get module file name function. The get module file name function, in this case we want to, we can have it as W. Tries to find the file name of the module that is currently running or that's specified. If we put it to null pointer, it will try to find the module of the current executable. And let's make a buffer here, module file name, and let's make it maybe something like that. It's just probably too big, like something like normally you would take something like max path in here, but max path is also a bit the deprecated stuff. Module file name and max path in here. Yeah, let's use max path here quickly. And if we do that, we can quickly check how it goes. So let's quickly try to load a shader with our new code. So let's include shader here, and let's try to load a shader here before we create the pipeline state. Where is the pipeline state? Is here. So here we then basically gonna have our shaders. So how are we gonna load our shaders? Let's create a new shader, Vertex shader. And the name of the Vertex shader will be Vertex shader. And then we can also specify the pixel shader. And now let's quickly see how this goes. And what we got if we do it. We should break in there. Yeah, there we go. And now you can see that the module file name is actually my executable. That's correct. So now I want to convert this to an std file system path, and then I want to stripe off out the name. So std file system path. Let's call that one shader dir for shader directory. This is going to be equal to module file name, and then we can remove the file name from that shader directory, and then we should be left with just the directory without the .exe extension. So let's see if that works. And now we have the shader dir. It's a bit hard to see, but we can go into the text, and yeah, it is our binary directory. So now we have that shader dir composed. Now what I want to do is I want to have that as a static. So inside of here, I want to have a static std file system as shader dir. Now this is static, so it needs a bit of initialization. Std file system path shader dir, which is in shader dir. Now this should have a instance. And now the only thing that I want to check is, first of all, that one is going to be assigned, and then we're going to remove it, and we're only going to do it if as shader dir is empty. So if this is an empty path, we're gonna retrieve it so that we're gonna not get it. Actually, we could make it even even simpler without having it inside of here. So we could just do it like that, and if it's empty, do it in here. And then here's the shader dir here, so we don't need to have that global instance, which is a bit cleaner, I think, and we don't have it polluting us here as well. So that seems good. That is a bit better here to have it like that. And then what we want to do is we want to basically now compose a final directory path out of that. So we want to load from that file. So fstream for file stream is what we need. And then we can do a if stream shader in, and shader in will be composed out of the shader dir, and then we're gonna have the file name. And actually, if we do it like that, we don't have the extension in here, so we would need to make it like that, and then should be able to change the. It's not really doing what it should do. Like this is composing a new path. Okay, so we just need to adapt the file name here to also have the .cso extension. So vertex shader.cso, pixel shader.cso. It's okay to have it in here. It makes our code here a hell of a lot better. Now then we have the mode as the iOS in. I think we don't need it if we have an in-stream, but what we need is binary here so that we have it. And then if shader in is open, we're gonna quickly check how big the file is. So shader in seekg to std ios end, I think. And we should also have an offset here. So offset is first, and then the way is used to 0 from end. So we are at the end. So now auto, or actually now emp size is equal to shader in telg, and then we want to seek back shader in seekg distance 0 std ios back for begin. Now we have the file size. Now what we can do is we can say m data equals malloc of m size. So now we have the size in here, and if the data is existing, we can now say shader in dot read. And we want to read to m data, cast it to a char pointer, and we want to read m size. All right, so now we should have readed the binary data of the shader into a buffer. And now I want to write an inline const void pointer function, get buffer, const return m data, semicolon, and then we're gonna have that here as well, size t, get size, and we're gonna return the size. All right, so now we have a bit of boilerplate code to load shaders. Let's quickly see if that works. We're making a breakpoint here and see if we get some data in the shaders. And let's see. All right, we have a breakpoint here. We have the vertex shader. You can see that there is some data to it, and there's also a big size in here. The pixel shader as well. So there's a pointer, and we have some data, which means that the shader seems to be valid. If it is valid, we don't know yet. We're not going to know until a few videos, but just the madness that we have. And maybe it's better to make it like that if we actually define the block. Now, the only thing that we want to do now is we now need to describe the shader. You can see that we have described the input layout here. And now we need to describe the shaders. So, for example, what we want to define is the vertex shader. And the vertex shader has a shader bytecode attribute, which is the vertex shader dot get buffer. And then we want to also get the size. And this is all written in here. So now we have like a vs.bytecode length, vertex shader get size, and p shader bytecode is get buffer. So we're basically gonna provide these two members to a member of our struct. And we can do this for the vertex shader and the pixel shader currently. And then what we're gonna have in between here is kind of like the rasterizer. And then down here we have our output merger. Right, so that's actually everything that I want to do for today. We now know how shaders work without having used them. Now let me quickly summarize because it is a bit confusing maybe. In general, shaders are just pieces of C++ code running on the GPU. They are compiled by a special version of the Clang compiler to a so-called bytecode that the GPU, or better to say the driver, can understand and turn into native code for the GPU. The code that you write is completely like stateless and unstructured actually. You can like put your variables where you want them. You don't need to specify any layout. You just write code that is like functional. And to bind it to the actual meaningful values, you need to define the semantic names after a colon, after your variable. So you write your variable, a colon, and then you write your semantic name. And these semantic names are mismatched to mix and match together. Now these semantic names can match across shaders. So if you have one shader that defines a semantic name and the other one that defines a semantic name, and the one returns kind of like a variable with that semantic name and the other one consumes a variable with the semantic name, they are linked together. The input assembler that we have used in the last video is describing the initial state of your vertex for these semantic names. So it describes the initial data layout of the vertices, including the semantic names that the vertex shader then can bind to. If you are using any shader after the vertex shader, it is required that the vertex shader is specifying the semantic name, or that isn't even like limited to shader, also to like components like the rasterizer. The vertex shader needs to specify all these relevant data. If the relevant data is not specified, it's not passed on through the pipeline. Now this chains together as you want. If you have a vertex shader and a geometry shader, the output of the vertex shader, the semantic names of the vertex shader, are being passed on to the geometry shader, and the outputs from the geometry shader are then, for example, with like SV position, passed on to the rasterizer. The rasterizer is going to rasterize and it's going to use these semantic values, and it's not going to discard them or consume them. It is going to still preserve them because it's still kind of like the same layout that's flowing into the rasterizer, which will also flow out of the rasterizer. The end of the pipeline marks the output merger. The output merger requires also a few system value semantics. In this case, the SV target is also the only one that's really required. The SV target in this case depends on the size of the render target, in our case a 4-component render target. And this is now the final purpose where we specify a color of a pixel. So in general, vertices here, pixels here. Even through the pixels are also like the same construct and still like containing vertex data. Now the GPU uses special data types, for example float 4, which means a 4-component float, and as you can see in the vertex shader, I can access them by XY, or for example RG, or RR, or GR. Okay, I'm gonna stop making funny noises. So in general, we can construct them with a special constructor that can take like any arbitrary data that might be available there. And what the output result is gonna be a colored pixel, colored data, and everything is fine. So that's it for today. I hope you enjoyed. Thank you for watching. Make sure to like and subscribe, and have a nice day. Bye.